Assalamu alaikum. This is Akia Labiboni. So my set was A. And now coming to the question number 1, where I'm given an AVL tree which stores numeric values. I need to design an algorithm which efficiently returns the sum of all values within a given range. Now, since we are working with an AVL tree, which is a balanced binary search tree, we can use its concept or structure to make our algorithm efficient. How? Well, in a binary search tree, the left the left subtree has all the values smaller than my root node, and my right subtree has all the values greater than my root node. So the AVL tree follows this concept, and this can make our algorithm efficient. So for the algorithm, the input would be the root of the node, and L and R for our range, and L and R are both inclusive. So what would be the output? Output would basically be the sum of the values of all the nodes that are within L and R. And the algorithm will be recursive as we need to compute the sum repetitively. Now starting at my root node, here as it is I'm starting at my root node and I need to check. So as we are using a recursion algorithm, I need to have a base case, and here my base case is that if my node value is none, then I will return 0. Otherwise, what if my node value is less than L? So if it is less than my L, my first starting of my range, then I would omit my left subtree and send my right subtree along with my L and R to the same function. Similarly, if my node value is greater than R, then I would omit my right subtree because all the values in my right subtree would be greater than that. So I would send my left subtree, L and R to the same function to compute my sum. Otherwise, my node value is within my range, and we will add this value to our sum variable. And this is how recursively we will traverse both my left and right subtrees to get the final sum. Now, if you see this an example, here 10 is my root node. Now, 10 and the L and R is given as 7 and 15. So at first the root node is within my range. So I'm taking it in my sum. Next, my left subtree 6 is not within my range. I won't take it. 2 is not within my range, but 8 is within my range, so I would add it. And my right subtree, all are greater than my range, all are greater than my R. So 16 and 20 won't be taken. However, 16 have a null, so here 0 would be returned. And finally, in my sum, I would get 18. Now, how is this method efficient? Well, as I said, it uses the binary search tree concept. So we can basically omit the subtrees that in which my values might not be there. Instead of visiting each node, taking more time, we are omitting the unnecessary part and only traversing those necessary subtrees. So as a result, this reduces time complexity. Now, what if each tree update must propagate features for downstream ML models? Then I would use a publish subscribe architecture. Why? So that basically the updates to the tree are sent asynchronously to the models without blocking the tree itself. And this PubSub architecture basically can handle an increasing number of senders and messages and also reduce latency. Well, how? Well, the AVL tree does not need to wait for the downstream ML models to finish processing the updates. Next, I would use a batch processing to accumulate and process updates periodically. As a result, reducing my overhead. Now, at last, I would use causal consistency because This ensures that my updates are seen in the correct order, and this is very critical for maintaining accurate downstream model behavior. Because if any if it is not received in a correct order, then there might be inconsistency in data. The model might get wrong data, and as a result, having a wrong calculation. So next, coming to the question number 2, where I have to store and retrieve large model weight files distributed across a database. So how does a basically B tree supports fast search and insert operations at scale? Now, what is a B tree? A B tree is basically a balanced search tree, and it is designed for systems where disk access is expensive. Suppose here databases. But unlike a normal binary search tree, B trees can have multiple keys in a single node, but the keys are in a sorted manner. So my B tree follows binary search tree concept, that my left subtree would be smaller than my root node value and my right subtree would be greater than my root node, but it can have more than one keys in a single node. Now, how this is beneficial? Well, it means that in a single disk read, we can load an entire node or a whole block of sorted keys instead of reading many small pieces of data. And a B tree holding multiple keys, its size corresponds to a disk. Each node basically corresponds to a disk block or a page. So the disk read and write operations are expensive. In a binary search tree, we can have only one value in a single key in my node. So we need to perform more number of disk operations or more number of disk read, which basically results in more expensive. But in a B tree, in a single disk read operation, I can read multiple keys from a single node. So this reduces my disk operations, and it might look simple for a small system, but at a large scale systems, this frequent disk read write operation becomes a major bottleneck. Now, even though there are multiple keys, as I stated earlier, the keys are stored in a sorted manner. So what if we need to search, and how B tree are faster in terms of searching and insertion? So if we need to search, we can only explore the relevant branch, because as it follows the binary search tree concept, we can just omit the unnecessary path by checking with the value, like whether it is greater or smaller, and this gives us logarithm time complexity. Now for the insertion path, as the single node have multiple keys, there is a limit. There is a capacity that how many keys can a node contain, and the maximum number of keys depends on the minimum degree t, where a node can have a maximum of 2t minus 1 number of keys. So if the node becomes full, then what it does is basically splits into two parts, but around the median key, and here the median key moves up to its parent node. So what if the parent node is also full? Then the same procedure is followed, but it is ensured that even we are inserting or deleting a data, the tree follows all the B tree properties. The keys are all in sorted manner, and it follows the binary search tree property. So even though it takes extra steps to insert new data like splitting and all that, but due to the logarithm growth of the tree, and as we can get access to multiple key at once, the disk operations are minimized, and hence the process is faster. So we can So if we need to store and retrieve large model weight files that are distributed across databases, P3 is still efficient in terms of search and insertions. Now, the next part, that how does this apply to a feature vector lookups? Well, in recommender system, what are basically feature vectors? Feature vectors are numerical representation of users or items. And when a user requests something, we know we need these feature vectors. So these feature vectors are stored as numerical representation so that the model can understand these values. What are those meanings? So this actually represents the preferences of users or qualities of items. And later on, model uses this to compute the similarity and then finally recommend to the user. Now, when a system needs to look up for a vector, a B-tree helps to locate the vector corresponding to a given user or item ID quickly without scanning the entire dataset. It does not need to scan my entire large dataset, so it can omit the irrelevant part, so it can easily fetch data, and this later on speeds up the similarity computation as I'm getting the requested data faster, so I can move to my next step, thus making the recommendations more responsive and efficient. Now coming to the question number 3, where I need to design an algorithm for finding a minimum spanning tree in a distributed system. Here, as it is a distributed system, it is assumed that no single node has the full view of my network or topology. So each node only knows the weights of its own incident edges and the total number of nodes in the system. Now, what are nodes? Well, nodes here are basically machines, and edges are communication lines, and weights are cost to move the packets over communication lines. Now, we need to cover all nodes by covering edges such that the cost is minimum. So the first question comes that why do we need a minimum spanning tree in this distributed system? If we think in terms of example with real world scenario, suppose we need to go from Uttara to Bhatta. So I have multiple ways to go from Uttara to Bhatta. I can choose expressway elevator, I can choose through Kuril, or I can choose through Gulshan, but I would obviously choose that path that would give me less, that would help me to reach my destination in less time. So similarly, the system is distributed, and from node A to node B, or from each node to other node, I can have multiple ways to communicate or transfer my data over my communication channel or line. Now, I need to choose the path which would basically give me the minimal cost to send my packet. So if I need to send my packet from my node to another node, I need to see that which path gives me the minimal cost. This is why a minimum spanning tree is required in a distributed system. So how does the basic algorithm works? Here the algorithm works at level, and at each level we can think of it as a collection of spanning tree, which basically represents a spanning forest, and each tree would have a leader. Now why do we need a leader? The leader would represent that fragment, and as we are creating smaller fragments or collection of spanning tree, we need to merge those to create a single minimum spanning tree. So we can use this leaders to merge, and then at last create a single large fragment. So at level 0, each node is basically a spanning tree itself, and it is the leader itself of its own fragment. Now, each node within its fragment sends a search message. Why? Because it needs to know the minimum weight outgoing edge, which is also referred as MWOA. So, once the minimum weight outgoing edge is identified, nodes exchanges messages between them. Like to coordinate merging with their neighbor fragments through these minimum weight outgoing edge, and it helps them to differentiate the nodes which are inside their fragment and which are outside their fragment. So after it has find its minimum weight outgoing edge and the chosen minimum edge fragments are connected and merged into larger fragment, here two cases might happen. As I said, it is working on a level based. When we are merging two fragments, the fragments might be at same level. So if they are same level, their level is incremented. But what if they are at different level? Well, if they are at different level, then the merged fragment takes the higher level. So this process of finding the minimum edge and then merging is repeated until when? Until a single minimum spanning tree is formed. So my termination condition for this algorithm is when all nodes are part of a single large fragment and representing the minimum cost required to move packets over a communication channel. Now, how can we, well, or where can we use this minimum spanning tree in real world machine learning scenarios? In unsupervised learning. So, in unsupervised learning, the labels are not given. So, clusters needs to form based on similar patterns. So, MSTs can help form clusters without knowing the number of clusters in advance. Then in this ML distributed system, if we need to set up a data center, MSCs can be used to reduce the overall communication cost. So we can, as I said, we can choose the we can choose the path which would result as minimum cost. And another interesting point is that for feature selection. So if we represent nodes as features and correlations as edges, then by using minimum spanning tree, it can help to remove my redundant features. How it can remove the high correlation features. And and real world example of this is that gene selection in genomics, like to identify key biomarkers, or in my sensor network optimization, where it can help to say that which sensors provide redundant information. At last, in outlier detection, which is very important in a machine learning pipeline, and as the edges would have weights, and the unusual long or larger edges in the minimum spanning tree can point to outlier. Now, coming to my next question, number 4. Here, if we compare slab allocation versus garbage collection for a tree or graph-based feature index and given my memory constraint environment, so basically, slab allocation pre-allocates fixed size memory chunks or slabs for objects, and garbage collection aims to recycle the unused memory automatically so that the heap memory does not run out of space. Now, if we compare, the tree traversals and node allocations are faster in slab allocation. Why? Because the latency is predictable. And in garbage collection, it causes unpredictable pauses, and this might interrupt my tree traversal or cause delay. Moreover, in slab allocation, there is minimal fragmentation, so it makes it suitable for systems with tight memory constraints. And in garbage collection, it is not efficient as it adds overhead and also might not reclaim memory promptly, especially if my graph has a cycle. So if we compare these both, and which supports better predictable latency for online serving and ML system, well, slab allocation supports better predictable latency. Why? It takes of one time, like constant time, to perform memory operations and does not introduce any unpredictable latency or any pause. And this is very crucial because suppose if we think for a recommendation system used by Netflix, then slab allocation is often preferred in these systems to store frequently accessed feature vectors or embedding graphs efficiently. Why? Because this ensures that when a user requests a recommendation, the system can fetch and score features in very short span of time, in milliseconds, without any unpredictability that is caused by the garbage collection pauses. So, slab allocation supports better predictable latency for online serving in machine learning systems. That was all. Thank you.